Hi, everyone. Today, I want to share with you what we learned about the challenges of using biometrics and continuous user authentication and why we still recommend using it. My name is Tamas Zelczer, and I'm the CEO of Cusrsor Insight. Cusrsor Insight is a startup specializing in human movement analysis. Our core machine learning technology is basically able to break down human movement into hundreds of thousands of features, and then we can use that for pattern recognition. And we're using this to authenticate people based on their handwriting or cursor movement biometrics. Currently, we're serving about 2 million users. And so continuous biometric authentication, of course, we find that it's very exciting, but there are some very unique challenges that don't exist for other types of authentication methods. And these are the challenges that I want to talk about today, what we've learned during our journey. And I think it's very important to understand these for someone that wants to implement and use a biometric continuous authentication system effectively. So let's start with some bad news. And I promise that in the end, I will finish with some good news. So biometric authentication is never going to be 100% accurate, and regardless what other people tell you. So with passwords, it's either going to be, if you type in your password, it's either going to be right or wrong. It's never going to be a maybe. Whereas with biometric authentication, the result is always probability on a scale between 0% and 100%. So it's pretty much always a maybe or a very likely or not very likely. And all these probabilities are actually influenced by a lot of factors. Some of them are completely uncontrollable and are changing all the time. And so, for example, even with face recognition technology, if your twin is present, then suddenly it's not going to be so accurate. Or if you've ever tried to use a fingerprint ID while eating chicken wings, then you notice that this is just not going to work with greasy or wet fingers. So even if a biometric authentication system works well for a given person, it can always make mistakes. And continuous authentication, what it means is that we authenticate the user throughout the user session. So we just repeat authenticating the user all the time, which means that these mistakes can happen all the time as well. And so also biometric authentication is never going to be equally good for each person. This is quite a famous example showing that face recognition technologies work significantly worse for women and also for people with darker skin. And it sounds awful, but of course there's nothing sinister in this. It's just the way it works. And there can be many reasons for this. These systems are very complex, but the main takeaway here is that even if there is an authentication system that works at a certain level of accuracy for on average for the whole population, there will always be groups of people or individuals for whom it's going to be a lot better, and for others it's just going to be a lot worse. There's very little to avoid this. And okay, so biometric authentication is not perfect, but then how do we know if it's good enough? So what is considered a good accuracy for an authentication system? That's obviously a very common question, and it's actually very difficult to describe the efficiency or the accuracy of an authentication system with a single number. The standard method of measuring these systems is actually using two numbers: the FAR or false acceptance rate, and the FRR or the false rejection rate. And and these are actually the two types of errors that can be made by an authentication. I'm sorry, I'm going to start this slide over. Okay.
Yes. Yeah.
Okay.
Started this slide.
Okay. Okay. So we know that biometric authentication is never perfectly accurate, but then what's considered a good enough accuracy? That's a common question, obviously. And a single percentage figure is usually not enough to describe the accuracy of a system. And the most common values used to measure the accuracy of an authentication system is the FAR and the FRR, or false acceptance rate and false rejection rate. And these are the two kinds of errors that we can make. So either accepting the wrong user or rejecting the right user. So for example, a 20% FAR means that 20% of the time the system will mistake someone else for the genuine user, and a 20% FRR means that the system will reject the genuine user once out of every 5 attempts on average. And it's important to note that FAR and FRR work against each other. So you can actually adjust the acceptance threshold and increase one and decrease the other. So there's also a certain level where the two lines intersect. So where FAR and FRR are equal, it's actually called the equal error rate, and some people use that to describe the accuracy, which makes it easy to compare systems, but by no means does it mean that that's the lowest achievable accuracy for a given system. And of course, there are other many sophisticated ways to describe the accuracy of an authentication system, like the cost of log likelihood ratios, which sounds sophisticated, and it is. I'm not going to go into details, but what it mainly does that it takes into account the size of the mistake made by the system. So if it was, it thought that a given user was me, whereas it wasn't, then it also matters how sure it was that it was me. But in fact, I wasn't. So something to keep in mind is that if an error rate that someone claims, it can be just made up, or of course it can be based on some measurements. And this error rate is 0.0001%. I've actually seen this claimed by a handwriting signature verification vendor. And so first of all, being able to calculate such a low error rate means that you would have to make over 1 million individual tests involving, in this case, hundreds of thousands of people, which of course no one has ever done. And also, this accuracy is actually better than using DNA testing, which is of course the most accurate biometric identification. So just be aware of anyone claiming some accuracy ratios that just look too good to be true. So getting back quickly to the FAR and the FRR, a good or a desirable accuracy of a system can actually change from use case to use case, and sometimes it's better to make one type of a mistake than the other. So for example, if you, which is an extreme example, if you authenticate someone who can launch nuclear strikes, then of course, it makes sense to put that FAR really, really low and make sure there is no false acceptance happens, even if that means that for the right person, it's actually quite difficult to authenticate themselves, and maybe they will have to try more than once. On the other hand, if you're authenticate users who are logging into their video chat application, and there are very few fraudsters anyway, and even if they get in, the worst that can happen is that they maybe make a prank call. So in that case, it makes more sense to maximize the user experience and decrease the false rejection rate, meaning that it's easy for the genuine users to get authenticated, even if that means that those very rare intruders get in higher numbers, who are in this example anyway harmless. So the main point here is that try to get an idea of your expected genuine and fraudulent login or user login attempts or users, and also try to figure out the cost of each type of error, so the false rejection and the false acceptance. And once you have these numbers, you can actually calibrate an acceptance threshold so that you minimize your total cost of the mistakes. And now I'm going to talk about how we built, or what we learned during building a continuous biometric authentication system. And so it's it wasn't an easy task, and it's actually not very easy to make it accurate, especially if you want it to work well for the first time. Three big categories of the factors that influence how accurate a continuous authentication system can be is the amount of data, the quality of data, and the fact that what you're actually trying to measure, those kind of human behaviors, biometrics, are not stable. They kind of change all the time, and I'm gonna talk about that later on. But first, let's move on to the amount of data. So one phrase you will never hear from a data scientist is too much data. And of course, it's obvious that the more data you have, the better the chances that the authentication system will work well. And there are two phases of an authentication system, or pretty much any machine learning-based prediction model. And the first is the training. So it's important that during the training of the system, you have data from as many different people as possible and as much data from each person as possible. And so without doing the training, the authentication is not going to work, because the system will have to know who you are and how you look like, or in our case, when we're dealing with cursor movement analysis, how you move your cursor. And then when you already build the biometric profiles and you do the actual evaluations, then it also really matters how long time you have, or how long the movement samples are that you can work with when you are making your authentication decisions. And so this is just an example that so once you build the models, you can run different simulations and tests. And in one case, we just looked at what happens if we shortened a little bit the movement samples that we fed into the system by 40%, and then it resulted in as you can see, a 68% drop in the accuracy, which is of course a huge trade-off. So of course we didn't opt for it, but it just shows you that it's again very difficult to talk about the accuracy of these systems because they will depend on just so many factors and circumstances. Okay, so next topic is the data quality, which is obviously very important. Someone's trying to build or operate an authentication system. So unfortunately, the movement sensors that are out there, the computer mice and the touchpads, just really don't report movement accurately. They're just inconsistent. So on this video loop, what you can see is actually our DIY testing station that we built in our office. And yes, it is a turntable, and on top of it is a signature pad, and there is a stylus attached and some weights that simulate the hand pressure. And the point of this exercise is to see, so what we're expecting is like really consistent circles with consistent speed and consistent weight. And you know what we found when we did these tests, that it almost never happens that you get the data that you expected. So these actual measurements are way off compared to what the manufacturers claim. And we actually wrote about this in our blog. It's interesting stuff. If you're I recommend it if you're interested in reading it. If you're interested in the quality of these kind of devices. So once the data has arrived from the device to the computer, then it's time to deal with the software generated issues. So unfortunately, moving the cursor on the screen is not really a high priority task for a computer. So that means that if the processor is busy running other applications or viruses on your computer, then that's when the mouse cursor starts to skip or drag, and that is of course really bad when we're trying to analyze the movement of the cursor. And even if everything works well and there are no hardware and no software issues, which is of course never the case, then the fact that biometric movement is just noisy by nature makes makes things hard. So I will talk about that a little bit later. And now let's move on to some examples that we've come across, some data quality issues during our work with biometric authentication. So on the left-hand side on this slide, what you can see is someone trying to just draw a continuous wave, and the red dots are what the computer reported. So, and of course, and the line is our algorithm just connecting the dots basically. And what you can see that, of course, it's not a continuous wave because there are a lot of points missing. So that's an obvious mistake. Also, if you look closer, you can notice that some of the dots come in groups of 2 or 3. So, for example, in this middle segment, you can see these groups of 3, and again, that's just completely unnatural, and so no one moves their hand like this, slowing it up and spinning it up again all the time while just drawing a straight line. So this is also very obvious data reporting issue. And on the other side, on the screen, on the right-hand side image, you will see data points being recorded in order from top to bottom. And the first number is the timestamp, and then come the coordinates. And in the red boxes, you can see that the timestamp actually decreases. So as if time was going backwards, which is again, obviously, not happening. So this is just, again, an incorrect reporting. And the bad thing about this is that this is very easy to spot. But once you know that it's unreliable, you cannot be sure that the other timestamps are correct. And timestamps are super important because we're trying to calculate speeds and acceleration. So if those are off, then obviously your input data is going to be off as well. And so on this slide, you can see the reported cursor speed on the left-hand side and cursor acceleration on the right-hand side. So it's the red line that is the reported value. And again, I mean, you don't need to be an expert to figure out that this just looks completely unnatural. So on the horizontal axis is the time, and on the vertical axis is the speed and the acceleration. So you just cannot change so quickly. So again, this is also some kind of reporting issue. And again, the green line here is the correction, which already looks a lot more natural. And on this slide, what you can see is called angle snapping, and that is it's actually a feature of operating systems. So if you ever try to drag an item on your screen across it in a straight line, then you can find that it's actually very easy to do, and that's because the nearly horizontal and nearly vertical lines are snapped to completely horizontal and completely vertical. By the way, the same thing happens if you're trying to draw or write on an iPad. And here you can see that the red lines just again look unnatural when someone was trying to draw some ovals here. So angle snapping used to be an issue for gamers as well, for first-person shooter players, but that issue has been corrected in most games already. So most of the quality issues can be dealt with. I mean, it's a very common occurrence in any part of data science. So there are tools like the Kalman filters and other smoothing algorithms that can be used to correct most of the incorrectly reported data by the hardware and the softwares. But of course, there are some edge cases that are hopeless. And again, this is a real example from last year. We were collecting cursor movement data from various remote computers, and this user was running this Windows NT4 operating system, which is more than 25 years old. So probably the computer was not that much younger, and I mean, it's a miracle how this person was able to actually surf on the web. But as you can imagine, like the cursor pretty much moved like once every second, and even then it jumped from one side of the screen to the other. So obviously that's completely hopeless when you're trying to use that cursor movement data to basically analyze the movement dynamics. So we've already discussed data quantity and data quality as important factors, and here we came to third and last factor, and which is the fact that humans are not machines; they don't move like machines. Even the same person, the same way you can never sign your name twice exactly the same way. You cannot just move the mouse in the same way all the time. So that there will be some differences that these kind of authentication algorithms will have to deal with. And this is just a short list of the factors that influence cursor movement. You can think of a person walking, and you will notice that these things will also be very visible in the way a person walks. So mood, obviously, if you're in a good mood, typically you will move more dynamically, as if you're in a bad mood. The body position is very important. So when you're moving your mouse, are you sitting in a chair? Are you standing up? Are you lying on your sofa? Is your elbow on the table? Have you just crossed your legs and pushed your body weight? So these all influence the actual cursor movement that we have to work with. The surface under the mouse. So obviously, if you're using a mouse pad, the mouse is going to be moving differently than if it's on the tabletop or if it's on the bed sheet. Ambient temperature, so if it's very cold, your fingers can get a little bit stiff. You're going to be moved differently if you're excited or anxious, or if you're in a depression, an injury, even if you just carried a heavy bag before you were browsing the web, your arm's going to be a little bit more stiff, and your movements are going to be just a little bit different. And then, of course, hormone levels. So it's for almost everyone. It's true that in the morning they move more dynamically. Then after a big lunch, they will slow down a little bit, and then after the afternoon coffee, they will speed up again. And of course, there are the drugs and alcohol in someone's system will obviously very much influence the cursor movement. Just as seen on this image, which is a real image, by the way, of a real experiment of spiders making webs under the influence of different drugs. We didn't do this experiment, but I found it cool, and it kind of, I think, illustrates the point. So to conclude, building or having built a continuous biometric authentication system was not easy, very rewarding, but it's actually still, we recommend using this kind of tools. There are a lot of advantages. First of all, these authentication systems continuous authentication systems are invisible, so there is no impact on the user experience. Of course, it's more secure to authenticate someone during the whole user session than just at the beginning, because account takeovers can happen anytime during a user session, or computers can be left unattended anytime. And also, there are some critical applications that not really require a separate login. So, for example, your desktop email application, if you just want to use it, you don't need to log in to it, but it's still good to make sure that the actual genuine user is reading and writing the emails. Also, an advantage of biometric authentication is that it identifies the actual person and not the device. And many authentication methods, like a one-time password sent by a text message or some device fingerprinting methods, actually identify the device and not the person. Of course, devices can be borrowed or stolen, but not your biometrics. It's pretty hard to steal your biometrics. And even if it happens, it's really even more difficult to impersonate someone or replicate someone's movement biometrics. And so the good news is that I don't think that anyone needs to find the best or the ultimate authentication solution, because the good news is that these different types of technologies can be layered on top of each other. They can be combined, and together they can strengthen the accuracy and effectiveness of an authentication system. And I mean, after all, that's what we all want: a secure, efficient, and convenient authentication system. So thank you very much for your attention. If you have any questions, feel free to drop me a line. Thanks again.